Good afternoon and welcome to Mirabilis Design's webinar on architecting autonomous driving systems. I'm your host Deepak Shankar and I'll be spending the next 45 minutes walking you through the VisualSim solution for designing autonomous driving systems. Today we have a control panel on the right hand side where if you click on the top bar you can see that there's a chat window. Feel free to type in any of your questions and we'll answer them in the order that we receive them. We might even try to integrate them into the presentation. With this, I would like to get going on the presentation. Welcome to one and all that have taken the time to attend this presentation. I know it's fairly late in the evening for many of you. Agenda today is we're going to talk about the problem statement, what are the challenges, how do we address the challenges, and then we're going to dive deep into a variety of analysis or studies, case studies. In this case, looking at the exploration of network and hardware attributes, hardware-software partitioning, correctness of the software in the sense of, is the sequence correct? Is it meeting its timing deadlines? Is the power consumption within the range that's expected? And finally, talking about custom control, things that would enable you to better define what your communication is with the MEMS devices that might be in your design. Why do we need system simulation and driving systems? Today, there's a number of tools that help you do your implementation. There are RTOS based tools that allow you to test your software. There are tools from Vector that allow you to configure your network. But what is really missing is something that actually gives you visibility over the entire vehicle network. So it's the ECUs, the RTOSs, the hardware, the accelerators, the software, the network, everything combined, because you need all of it to really aim that your final vehicle verification is going to actually work. And also, when you're writing out these specifications, you want to be able to analyze it to make sure you don't have any bottlenecks or you're really meeting the highest reliability that is required. So really what we have to do is you really need to simulate the entire system and make sure that all the configurations are correct. I mean, there are other aspects also that you may want to look at, which are your safety and your operational goals as well. What Mirabilis provides is a rapid prototyping platform for the entire system. What this means is really an environment where you can actually combine your network, your operating system, your use cases, your traffic, your software, everything within a single environment. The reason for doing that is then you can actually simulate all of it and be able to look at the timing deadlines, look at what's the throughput, what's the utilization, what's the power consumption. A model such as this would look like this in our environment. What you're seeing over here is a CAN network which can be CAN FD as well. We support CAN FD, and you have a variety of traffic, power. All of this information is built into this model that allows you to construct the entire network. So in this case, for example, there's 2 cameras and 4 radars. Now, what also gives you the ability to define your entire hardware platform. In this case, we've got a CPU and a GPU. We've got the power table associated with all the devices. We also have the triggers, which is your offsets, associated with activating the sequence of software tasks. Now, these software tasks are actually distributed across. If I go into one of these blocks over here, you'll notice they're actually distributed across a multi-core architecture where you can actually try to map them to different cores which are running concurrently. These masters are running concurrently, and you can look at what's the effective performance that I receive, what's the effective power consumption. So this is what I'm going to spend time with you in the next 45 minutes walking you through how this can be done in VisualSim. Now, why is the modeling in VisualSim so important when there's a lot of solutions that allow you to load your software on top of an ISS, or for example, have very detailed cable modeling or network modeling environment? Really, it's enabling you to do it at a lower level of fidelity than actually running the software code, but at a higher level of fidelity than a cycle-active process modeling. The reason is you want to integrate everything within the single environment, and that's the only way you can see you end to end. What we provide is really the platform and a series of parameterized libraries. So you can modify and change the values of the elements within the model. And one is you can quickly construct the model and then run a variety of Monte Carlo simulations to try to see what the performance would be for different scenarios, for different use cases, for different sensor profiles, things like that. And also for different network configurations as well. Now, what are the types of experiments that you could do in VisualSim? In this particular case, we're really only focusing on 5 experiments, the ones I talked about in the agenda, which is, first you want to measure the hardware utilization and response time for various combinations of sensor rates and data sizes. The next is you want to partition the drive and control tasks across multiple ECUs, which could contain a combination of processors, GPUs, and accelerators. Then you want to check whether your application sequence is correct. So if it's going to do task where the sensor data is sent out to node 3, does some initial cleanup processing like in a filtering or things like that, and then it's sent over to another node where the processor actually does some control data, and then from there it's sent over to the GPU to do some matrix manipulation or the artificial intelligence piece of the activity, and then it returns the data back to the processor, which could be on node 6, and then that one could send it back right back to the to the attenuator that actually has to do the control processing, or to the MEMS device. So is that sequence really occurring, and how much time is it taking for that entire sequence to complete? That is the main essence of what you want to do with experiments in VisualSim. Associated with that, there's a lot of attributes like what happens if I change my clock speed, what happens if I change my power management algorithms, or for example, I add a few more tasks like some diagnostic tasks or some additional functionality. Can my system still control? Can my system still be able to handle that load? A quick introduction to Mirabilis Design. We've been around for about 15 years now. We're really focused on system architecture exploration. We're in a variety of markets that allows us to be able to get intelligence and data from multiple markets to integrate that into VisualSim. For example, in this particular thing, we're in the networking space, we're in the semiconductor space, the aerospace, and automotive. So what do they give you? The semiconductor gives you, for example, the details of the SoC of the chip. The networking gives us, how the network would really behave and add things like distributed denial of service in terms of failure analysis. The aerospace industry gives us a variety of information, right? Reliability, resilience, things like that. And of course, the automotive is about looking at ECUs and looking at the network, the configuration of the ECUs for the network to feed in data and things like that. Why Mirabilis Design? We are the largest source of system modeling IP, and we also have considerable experience in this market for the last 15 years. So we've got a very large segment of the customer base that are using VisualSim on a daily basis. Now, VisualSim itself, as I showed you a few seconds ago, and I'm just going to go back to that window again, it's a completely graphical modeling environment. You have a series of libraries on the left-hand side. You drag and drop these blocks, these are called blocks. Drag and drop them, connect them together, and each one could have, as I showed you earlier, a unique set of parameters. And you can set the configuration for those parameters, and the block would start behaving like your proposed systems. And what you also have is an extremely high-performance discrete event simulator that runs at about 90 million events per second. And that allows you to run a variety of Monte Carlo simulations with parameter sweeps of a wide range of values. Allows you to do functional analysis, so looking at the correctness of your algorithms, performance, which is your utilization, your throughput, your timing, power in terms of energy, and also failure analysis, which I'll be talking about in more detail downstream. One of the things VisualSim does provide you is the ability where not only can you build models using our IP blocks, but we also have a custom development environment for anything that you want to build up maybe a proprietary algorithm like a queue management within your software, or for example, handling resources or timers within the software. You can model those using our custom development. Plus, we also have interfaces to third-party tools that you can connect up and use as part of the entire system. So they can be files that are like traces that you import from a real car, or it can be a C++ module that you can bring in. So a variety of tools that you can also integrate within the environment. That's your integration platform with all the libraries on top of it. This here is just the current listing of all the libraries that we have in VisualSim. This is an ongoing process as we constantly keep expanding. We get about anywhere from 2 to 4 libraries a quarter. So if these are not there, make sure to come back to us, and we can show you how we add additional information as well. Now, we talked about the end-to-end system. What really constitutes an end-to-end system? End-to-end systems in an autonomous driving vehicle is really about going from the sensor to the attenuator, and you trace all the flows through the system. So you test all your failure analysis, test all your bottlenecks, test all any denial of service, the diagnostics that flow in. So you have the ability to actually test it from end to end. So for example, if you take the braking system, you're looking at the gyro, the engine speed, the rotations, the braking, all of that gets connected together in a single model, so you can see what happens end to end. Now, from there, we go down to a subsystem, which is the ECU, where we can set up a combination of your communication, storage, and processing. So you test all the software activity in the system context and see how it's going to react for different data rates coming in off the network. And on the network itself, you can you either assign all the tasks on a single ECU or actually distribute them across multiple ECUs. So allows you to see whether if I distribute them and I have messages going across the network, is my system still going to be viable? Then of course the last piece is the semiconductor itself, looking at IP cores, looking at how do I configure on the system on chip the number of cores, the clock speeds of cores, the memory bandwidth, the backbone network on chip that connects everything together. So this is in a nutshell what we can do in terms of exploring the entire autonomous system. Now, in terms of architecture analysis with VisualSim, these are examples of the types of analysis or reports that we provide within the environment itself. So for example, we have things like timing deadline tools that we provide you, things like your batteries, your power algorithms. On the network itself, we can look at what has been the effective bandwidth consumed, so looking at quality of service, looking at the MIPS of the processor, looking at how much based on your hardware software mapping, what is the usage, and finally buffering, because that's one of the things that's key that a lot of times it's skipped as part of your system modeling, is looking at buffering at every part of the system, be it at your network transmitter receiver or your processor or your software, or even on your communication systems. I'm sorry, even on your storage systems as well. So you can actually look at effects of redundancy, failure, safety, and security. Now, the first aspect of our system is really about hardware-software partitioning, and what that means is really that I have a network, I have all these different systems that are connected together. When I say systems, I'm talking about all the ECUs connected across the CAN bus, and there's different functionality in each of the ECUs, like the engine, as I was talking about, the braking, the engine, the EPS, all of these. Now, what I can do is I can allocate each of these functions onto one of these physical architecture. So this is my functional or my logical mapping of how my tasks behave. And then here I can actually do the mapping onto this network itself. So the idea is to try to see what is the best configuration for my target application. See, that's the most important thing, is to look at it, not just that, hey, I've got space and I want to allocate it, but rather, what is the target application, what is the requirements for target application, and then working on the assignment. So for example, the system that we're going to take and look at right now is a design that we have done fairly successfully for a lot of customers, which is the, sorry, I got the wrong one. So right over here, what we have is a system that shows you these are all the messages and these are all the tasks, the rates, the time it takes, and things like that. And also it's got the mapping of which ECU these tasks are running on. So what I'm going to do is just go ahead and run the model. And what I'm going to see here is my range of latency. So you can see that the task takes somewhere between 0.6 and 1.8 seconds. So that's my processing latency from like 0.6 to 1.8 seconds. We're not going to worry about any of the other items here, but rather what we're going to do is we're going to come in here and we're going to replace it task 2. We're going to move it from ECU 3 and move it to ECU 2. So that way T2 and T3 are now running on the same core. Now what this does impact is that T2 is dependent on M1, for example, which means that the traffic on the network, the traffic profile on the network will also change. So now I'm going to go ahead and rerun the simulations to see what my latency is. So one thing you're going to notice right away, the bottom is still 0.6, but you're starting to notice that the peak is actually going up to 2.0. Notice that most of it is at the 0.8, but the other time is evenly distributed. But there's a long tail that takes you all the way up to 2.0. So by doing these changes, by reallocating them, I can see how these things get impacted. So for example, one of the things I'm going to do is, sorry, I'm going to leave out the network. I'm not going to change anything on the network. But what I'm going to do here is I'm going to move this over to 3. And the other thing I'm going to do is I'm going to make this one the higher priority. So right now it's got the lowest priority. I'm going to increase the priority and make them both even priority that run on ECU 3. I'm going to go ahead and run the exact same design again and see how it impacts. Notice one of the things is that earlier on we were between 0.6 and 1.8. We actually come back, but then the nice thing is most of the traffic has moved, or most of the latency has moved further to the left. So most of it is in the 0.8 again. So what this gives me is the ability to understand how the system is actually behaving. Plus, I get trace here to actually see what happens to each of these tasks in terms of the task here, the messages, the read buffers. You can see where it ended up. So you can see this was an ECU 3, this was ECU 2. So you can actually see as you go up where each of them were actually executing as well. So it gives me visibility into what is happening within my particular system. What exactly are the performance metrics, what exactly are the behavior of my system as well. Now, another area to look at is the diagnostic control of my hardware-software configuration, because one of the things is if the diagnostics have to meet the deadlines, the diagnostics have to meet their requirements to be able to sign off on your, say, your ISO 26262. And this is a very important requirement as part of your design aspect. Now, most people look at this more on the implementation side. With the VisualSim environment, we can look at it while you're doing your specification. So what does this really amount to? It amounts to something that looks like this. So for example, over here, I've got all my sensors on my network. I've got some of them have the ECU hardware, the RTOS, watchdogs, the communication. This is the transmitter receiver. But I also have databases that create the kind of the behavior of the tasks itself. So for example, this here is my list of tasks and which ECU they're assigned to. This one here, for example, is my schedule table. Sorry, wrong one. This one here is my that's my memory device right over here. Okay, that's my schedule table to tell me what these runnable tasks are and what are the triggers for some of them. See, like right here, the triggers coming from somewhere outside, but well, these are like events. This one has a dependency. So you can have a variety, and this one needs this data. So depending on what they have, you can set up different types of priorities and different types of dependencies for your particular system. Now, when I go ahead and run the simulation, I get a variety of different types of statistics. So for example, here, I get to see, and I'm going to blow this up a little bit so we can see it a little better. But what I can see over here is how many of them have actually exceeded their deadlines. So you can see all of these are actually above the deadlines. The other one is there's also some of these that have not met the deadline, meaning they're actually below the minimum value. So we expect the deadlines to be within a range. Here you can see these were above the range and these were below the range. So it kind of gives you a visibility into whether your software is actually working correctly based on the expected configuration that's right here. What this one shows me here is the power consumption. Why is this important? There's cooling costs associated with your ECU. If I change the offsets on my software, could I reduce these peaks here a little bit lower? Because my average here is only 1.4, but you can see my peak hits 1.9. Is there a way to reduce the peak on the power consumption? The other one, of course, shows me my utilization. So you can see processor 1, the average is about 35%, but processor 2, the average is about 85%. So there's a and both of them don't have much buffering. Actually, processor 2 has a little bit of buffering. You can see over here, it starts off at 5 tasks, but then it reduces pretty quickly. Processor 2 really has, processor 1 really has only about 1 or 2 tasks that are being buffered. So you can actually see what's the consumption of resources within my processor in my particular design. I can also look at here this shows me my the Q consumption. But here's an important one. This shows me for each of these 9 or 10 tasks, actually it's 11 tasks, what is the time at which these tasks appeared and whether they were executed on ECU1, which is red, or ECU2, which is blue. Now notice that this is the profile. Now what I'm going to do is I've got some memory faults and I've got some spurious executions right here. I'm going to turn on those and inject those faults into the system. I'm going to go ahead and rerun the same simulation, but now I've introduced some faults into my particular design and try to see what happens. As you can see, the profile has actually changed substantially over the previous case. So what this means, and also if you notice here, the runnable delays have also changed. The profile itself has changed. The number of ones that are not meeting the deadline has increased. Plus, this is another important one, the power consumption hasn't changed dramatically. They're still at the 1.4 average and 1.9. So the power has not been impacted, but the time at which they're scheduled and the latency has both changed substantially. In terms of processor utilization, there's not a significant difference as well in the particular design. So main thing is how long does it take to complete and when does it actually execute? That is one of the things that we've had to look at as part of this analysis when we were doing the failure analysis of this particular architecture. And that's what you're seeing here is your steady state and your one with fault injection right over here. So you can actually see a comparison between the two, and you can actually see how much the difference is when you turn on and turn off some of these faults in your particular design. There's a variety of faults that you can introduce into your system. Slow faults, which are like say for example, the coils in my generator, so which means the available power starts reducing. Or there can be software faults, like in the model we saw earlier, which is modified the task execution sequence or the offsets associated with them. You can have like link shutdowns. You can change, like for example, like one of the processors either slows down or completely stops working. can my system still operate? So there's also the fault injection that you can look at for your early planning as well. Now, moving away from the network, hardware, software partitioning, hardware, we're now moving into looking at the software system. So we're looking at opportunities. What are the ECUs that I can shut down such that I can save power? Or for example, how do I look at what is the effectiveness of say certain software algorithms that I've implemented, or validating these algorithms? There's really no way to do that with your current system except after you've written your software and you're running it within your environment, within your RTOS, and seeing what the performance is. But that's like really late in the game. You want to be able to look at it very early in the design process. So what you can do is you can create state transition diagrams of this kind, and then you can actually run the simulation of these and look at what's the effective power consumed, or the effective response time, or the buffering, or the usage of different tasks and things like that. So here what it's showing you is for all these different tasks, what time they actually executed. So one of the things that becomes important here is you can actually trace if one of the tasks is not completing within the deadline, you can look back and try to see what was the cause of the task not completing or finishing within the deadline. So for example, if I could take say one of these things here, say we take this runnable 6 over here, this one over here, notice there is this one over here, this, and all of these tasks are not able to start because of the duration of this task. So as a result of this task executing, these are all getting delayed, and that could relate to the timing deadline misses that you are having in your architecture. So it actually helps you trace what is the cause of the failure. So it's not just about, yep, something failed, but rather you can track it backwards and see what really caused the failure. So a quick look at, what does VisualSim really offer? Because of the ability for you to be able to do these analysis up front and be able to do all the refinements early in the design process, even before you start a development, you can in a sense be able to save a substantial amount of your rework time. So where you find the errors during development, you go back, you have to make changes and things like that. Also during proposal phase, you have a very clear understanding as to how your system is going to behave, what are the resources required. You get a complete laundry list of those items, and that ensures that you're able to deliver a really high quality and a reliable product. Now that you see the kind of the overview of the types of things that can be done in VisualSim, I'm going to move over to looking at how do you actually do it in VisualSim. What is the modeling methodology? So let's go back to the system we looked at, which was trying to look at moving tasks across the ECUs. So in this case, I've got 4 tasks: T1, T2, T3, and T4, and I've got the messages, 4 messages in this particular case. You can see that T1 triggers 2 messages that trigger T2 and T3, but T3 requires M3 and M4 before it can fire, and T4 just depends on T2 triggering M2. Now here you can actually see where the allocation of these tasks are, which ECU they are allocated onto. So now what we want to do is kind of assemble up the network. So this is my CAN network with all my bridges. I have my ECUs, and I've got we already know what our messages and our tasks are assigned to the ECU. So now when I go back to that design we were looking at earlier, probably becomes a little more clear to you in terms of what is really happening here, which is that I've got these different messages. Those are the read buffers, those are write buffers, so that's your entry and exit, and it says which CAN bus does it first get on, and these show you my ECUs and things like that. So what can I do here? Some of the things I can do here, for example, is I can change the task rate. So let's say, for example, we make this super fast, and the task time, rather than being for this one, rather than being 200, we can make it 600 milliseconds. So now same design, all I'm doing is just parameter changes, but I've actually modified that. I've incorporated more functionality within each of those tasks. And as I did that, one of the things that it came back and it said was ECU3, which by the way has only one task running. ECU3 actually failed because the buffer was full. So when I go back to my design right over here, you notice that oops, sorry. ECU3 right, ECU3 right over here has these two tasks, and as a result of the change in adding more functionality to it. Now notice here, I did not really change the rate, either the rate or the task time in ECU3. Notice they're exactly the same as what they were. I did change the task time and the task rate on ECU1 for this task, but then my failure occurred on ECU3. That's because we had the dependency. Remember that T2 cannot fire before T1 fires, and also T3 and T4 are dependent on T2. So T4 has got these tasks that are waiting to be able to fire, but they can't fire because we've got this T1 taking an extensive amount of time. So if I go back into my plotting here, you're actually going to see, sorry, wrong one. Here, you can actually see how the latency, earlier on we were seeing 0.8 and 1.6. Now it's actually between 1 and 4.0. That's my end-to-end response time as a result of just modifying one task. Not modifying all of them, just one task, and you can see how the response time has changed. So allows you to see if I add more functionality in one place, how does that impact the rest of the system? Does it really work, or it doesn't work, or is it causing failures, things like that. So allows you to get complete visibility into how my system is operating or behaving. So that's a key aspect of actually your distributed system, where you're able to see how, if I make changes to my design, how does it impact my overall architecture. And that's right here. So one of the things we can do over here is compare. I can change the clock speeds of the buses, or for example, I can change the rate at which the sensors are sending data, and I can see what the response time. In this particular case, I'm doing a comparison between 200 and 400 megahertz. You actually see in a lot of places, the 400 megahertz actually takes longer to complete than the one running 200 megahertz. So you can actually see what the performance of your particular design is for different scenarios, for different parameter sweeps as well. The other aspect which we're talking about is the timing. See, one of the things in VisualSim is we look at any design with a three-dimensional view. You got the power, you got the reliability, you got the power, you have the latency, and you have the reliability. So reliability is a function of your redundant systems, things stop working or they slow down in terms of clock speeds, things like that. Do I still meet my power and my latency requirements? So latency here in terms of, for example, I expected T3 to complete over here, but then it really completed over here. The reason being is I've got two higher priority tasks, T1 and T2 are higher priority tasks. Remember, we set the priority. High priority tasks that are preventing T3 from completing. So it gets preempted here, gets preempted here again, and finally it completes right over here. So at a significant delay, and that's what you saw in terms of the buffer capacity or the buffer overflowing. So allows you to not only see that something failed, but trace back to see what caused the failure. So this is a major analysis or major exploration environment that allows you to be able to quickly pinpoint what the cause of my bottleneck was. As I mentioned earlier, if you have any questions, feel free to type them in the chat window and we'll try to incorporate them during the presentation. Another aspect of it is your power measurement. See, one of the things that most people do in terms of power is they either take an average of all these states and put those up, add them up and give a number, or they take the highest one, add them up, and get a number. But since in VisualSim we're actually doing a power analysis while the simulation is running, we know what the power consumption is at every instance in time, and then we add up all the area below that to actually get what the average power plot is. So for example, here, based on the activity in the system, you can see what the average power is. Like we saw in our design, we were getting about 1.4 watts of power. Gives you visibility with a higher level of accuracy on the energy and power consumption as well. Now, how do you deploy something like this in using VisualSim? The deployment process is, first and foremost, you can assemble a top level system. In this case, it's a series of CAN networks with an Ethernet segment with with a bunch of devices connected, all of them. The key aspect of your design are the parameter sweeps. So like, for example, what's the speed of the CAN? So is it a CAN or is it CAN FT? You can look at what the Ethernet was in terms of the sizes of the data, in terms of, what's the clock speeds. But you can also change things like, for example, what is the sensor data that's going to go across each of the networks? What's the clock speed of the buses and processors on each of the ECUs? So you can vary all of those to try out different experiments. So within an ECU itself, so that was the top level. Within the ECU itself, you can have multiple processors. You can have what's called the use case or the behavior flow. That's the workload. And then that kind of connects you to your caches and DRAMs and other types of resources that are on the network. And of course, you can have parameters here that are configured to say, for example, how many CPUs do you want to run? What's the clock speed of different devices? So you can set up all those to be able to do a variety of analysis. Now, looking at the hardware, you saw the network or the overall system. You saw a high-level view of the hardware. But now what you can also get is a complete view of the complete hardware along with processors, accelerators, DMAs, the actual network. So in this case, we have a time-triggered Ethernet protocol, so it's a very deterministic time-based system. You can see here we have a coal-fire architecture. We've got a network. We've got the SRAM. We've got DMAs. So you've got a variety of subcomponents, and you can see all the different parameters associated with it. So you can actually try now integrate this very detailed system into a network model and run that in the context of the full design in terms of sensors and attenuators and things like that. If you remember, what we said was at a lower fidelity than the actual software, but then a higher fidelity than a cycle accurate processing model. And that is exactly what we offer you right here. So if you look at performance statistics, you can look at your end-to-end latency. What is the range? So this is on a histogram. This is just a time plot. This one shows you all your different tasks and your messages and when they were executed. It gives you visibility into that. So with that, I wanted to, hopefully I gave you a quick introduction as to what VisualSim can provide in terms of helping you architect your autonomous driving systems. Feel free to ask any questions and I'll be happy to answer any of them at this moment. There's a lot of other experimental models that we provide you, a lot of templates, a lot of support in terms of being able to analyze any part of your system. So if there's anything missing that I haven't shown you that you have a burning interest or a burning requirement, feel free to let me know and I can either do it right now or we can schedule a private session later on. Okay, so I see one question. I'm going to go back to the tool here. The question was related to this particular architecture. So one of the things that is of interest is trying to understand how accurately can you depict the use cases and the hardware system. So one of the things that we look at any use case is that it's a combination of 4 to 5 elements. So for example, here is the rate at which these use cases are triggered. The second thing is the details of the use case. For example, which processor it's running on, what's the priority. The other aspect of the use case is your task itself. So we actually have a profile-based instruction generator that can give you a good representation of your actual software without actually having to run your real software. Then, of course, we have the model itself running in full detail. So you got all the attributes related to the model. So with this, we can actually get very accurate representation of your entire system. So it gives you full visibility into what exactly your system is doing in terms of both getting inside visibility, like what's happening in the pipeline, what's the cache hit miss ratio, how much of memory is consumed, but also getting visibility into how much of power is consumed for each of the tasks. Gives you both of those types of visibility as well. If there are no more questions, with this, I would like to wrap up my presentation. You can always contact us at info@mirabilisdesign.com, and our representative will also be contacting you directly to understand if you had any questions or what you felt about the presentation. We might also ask you a few questions to understand how effective this presentation was, and if there was something else that you would have preferred in terms of the presentation itself. With this, I'd like to thank everybody for attending this webinar, and we look forward to talking to you in the future. Goodbye.